Well, hello, and welcome to Doc Onco's Physics. My name is Keith Onco, and today what we're going to be doing is looking at how to solve circuits that can't traditionally be solved with just Ohm's law, but need something else in addition to Ohm's law to help us to solve them. We're still going to be using Ohm's law, all right, good old V equals IR. We're still going to be certainly using that, and we're going to be using some of the things that we already know about circuits, but applying them in some slightly different ways. If you look at the screen here in the lower right-hand side, we see a circuit with two loops. It's a combination circuit because it's not just a parallel circuit, it's not just a series circuit, but one other thing is interesting about this circuit is that we don't have just one voltage source. We have a 10-volt voltage source over here and a 5-volt voltage source over there. And the question is, what do we do with these? How can we determine what the total current is, or the current in any one of the loops of the circuit? Well, this is where the Kirchhoff's rules come into play. And with Kirchhoff's rules, what it does is it allows us to solve or analyze multi-loop circuits with more than one voltage source. And the first rule, if we look over on the left-hand side here, is what we call the current rule. And the current rule is this, and it's very simple. The current entering a junction must be equal to the current leaving a junction. So if we consider point C up here and point F down here, junctions, right? What the rule says is that the current I1, right here, that comes from this battery, the 10-volt battery on the left-hand side, current I1 comes up, right? And it is traveling to the right, and it hits this junction point right here. Something has to happen to that current, okay? Well, we've decided that some of it is going to split and go down I3, right? So it's going to go in the downward direction, and that's labeled I3 here. And we've also decided that I2 will also be leaving this 5-volt battery, and it will also be entering the junction. Okay? And so the rule simply is the currents entering the junction and the currents leaving the junction have to be equal. So in this case, we could say that I1 plus I2, right, those are the currents entering the junction, have to equal I3, right? And that's the essence of the first rule. That's pretty simple, okay? The second part of the rule, or the second rule, is the voltage rule. And the voltage rule says, and again, this is something that we already know. We've talked about this in series circuits and parallel circuits, in that the sum of the voltage rises and drops around a loop must sum up to 0. Okay, so this is one loop here. All right, I'm going to draw a clockwise circle. This is another loop here. Okay, and we actually have one final loop, right? We have 3 loops here. We have the left-hand side loop, the right-hand side loop, and then there's a loop that goes all the way around. And I'm not going to, I guess I can draw that in there. Our entire circuit. So we have 3 loops. To analyze Kirchhoff's laws, we only need 2 of those loops, right? Because we have 3 currents, I1, I2, and I3, okay? In order to determine what those currents are, we're going to have 3 equations. So far, we've got 1 equation. We need 2 more, okay? So what we're going to do is we're going to develop 2 more equations looking at our circuit, and we're going to use the loops to do that. Now, we've already said, we've determined that I1 comes from our 10-volt battery and it flows into junction C up here. Okay, we've already said that. And we've said that I2 flows from the 5-volt battery also into junction C3, and I3 flows in a downward direction towards junction F. Now, are those actually the way that the currents flow? We don't really know, all right? But that's okay, it's okay if we're wrong in guessing the current directions, because what will happen is, if we're wrong, when all is said and done, and we've done all the math, the current that we get will be negative. All right? So if I guessed I3 to be in the downward direction, and in fact I3 happened to be in the upward direction, when we're done with the math, I3 will be a negative number. Right? If I3 is a positive number, then we guessed right. If I3 is a negative number, then we guessed wrong. So guessing the current directions, really, there's no harm, no foul done here. We just have to write an equation for how we think it's going to be. All right, so that's one thing we have to do. The other thing that we have to do is we have to decide which way in this loop, right? So again, I have the loop. I'm going to change the color to red here. I have this loop, right? All right, when I analyze my loops, I have to analyze them in a certain direction. I always choose clockwise. I always choose clockwise and the only reason I do that is for consistency. All right, I want to be consistent in what I do, okay? And it just makes it easier that way. So I always choose clockwise. So I've got my analysis direction, if you will, all right, for the loop on the left-hand side and the loop on the right-hand side, and those are the two loops I'm going to use. And I have my current direction, so I have my first equation as well. All right, so let's see if we can come up with a second equation here. And this is going to be using the loop rule that says the sum of the voltage rises and drops around a loop must sum up to or equal 0. So let's look at the left-hand side. I'm going to start with our battery, right? Here's our voltage source. When we're analyzing in a loop, right, we have to take the direction of our analysis into consideration. It's very important. So when I'm going to start, say, right here at the lower part of my battery, and I'm going to go from a negative part of the battery to the positive part of the battery, and I consider that to be a voltage rise. Okay? Remember, it says that the sum of the voltage rises and drops around a loop must sum up to 0. If I go from the negative part of the battery to the positive part of the battery, that's a voltage rise. If I was analyzing in the opposite direction, the counterclockwise direction, and I was going from the positive part of the battery to the negative part of the battery, that would be a voltage drop. Okay, but I'm not. I'm going in a clockwise direction, so I'm going from negative to positive. So it's a voltage rise, so this is going to be plus 10 volts. Okay, that's the first element in my loop. Now I'm going to trace around the circuit, right? So I'm going from my battery now, and now I get to this 5 ohm resistor. Well, what's the current direction? The current direction is in the same direction as my analysis direction. If that's the case, then the 5 ohm resistor will be a voltage drop. Okay, and what's that voltage drop going to be? Well, we don't know the number, but we do know that V equals IR, right? And so it's going to be 5 ohms, and I'm going to leave the ohm symbol out here because we're going to get rid of those in a minute when we're trying to solve equations, times I1. So this should be a negative sign here, so let's fix that. I messed up there. I apologize for that. All right, so I have a positive 10 volts because it's a voltage rise. All right. The voltage drop across the 5 ohm resistor is going to be a drop, and so it's going to be negative. Okay? Remember that the sum of the voltage rises and drops must equal 0. A voltage drop is going to be negative. Now I continue around my loop, right? I go back to red here. Continue around my loop, and I get to the 10 ohm resistor here. Okay? The current direction I have chosen for I3 is in the same direction as my analysis, so this is also going to be a voltage drop. So it's going to be minus 10 times I3. Okay, and then we continue around our circuit. Are there any more elements? No. And I come back to my battery. I'm done with that equation. And what does all this equal? Well, we said that it has to equal 0. Okay, so we're going to set all that to 0. All right, I've got 2 equations. I've got 3 unknowns. I still need one more equations. So equation 3 we're going to get from the loop on the right-hand side. Okay, where am I going to start? Well, I'm going to start at the battery again, so I'll start over here. Let's change this to red. I'm going to start right here again. But remember what I said. If I go from a negative to a positive terminal on the battery, I consider that to be a voltage rise. If I'm starting right here, I'm starting at the positive and I'm analyzing in a clockwise direction, all right? I'm going from the positive to the negative side of the battery. This is a voltage drop. So what do I have? I have minus 5 volts. And again, I'm going to leave the units out in a minute when we're just analyzing the equations themselves. So I start here, all right, and I've got a voltage drop going around the battery and going in this direction here. And now I get to my 10 ohm resistor, okay? Well, what's the direction of the current that we guessed, I3? It's in the downward direction. What's the direction of my analysis? It's in the upward direction, all right? If the analysis direction is in the opposite direction as my current flow, all right, the guessed current flow that I guessed at, then it is a voltage rise, okay? So this is going to be plus 10 I3. Okay, so I've got my voltage drop due to the 5 volt battery, my voltage rise due to the 10 ohm resistor. All right, I'm going to continue on in this direction here, and I'm going to get to my 4 ohm resistor, all right, still going in the clockwise direction. Well, let's see what we've got here. I've got my analysis direction going clockwise, or up at the top here to the right. The current direction I guessed for I2 is to the left. So this is also going to be a voltage rise, okay, because the current direction and my analysis direction are opposite. So this is going to be a voltage rise. So this is going to be, again, plus 4 times I2. All right. All right, now let's continue our travels around the loop. We get back to where we started from. We're done, okay? And now I can set this equal to 0. I now have 3 equations and I have 3 unknowns. So what do? Now we have to try and solve these equations, right? So we're going to do some substitution. Now at this point, you can say, well, I have a fancy calculator, one of the TI calculators, if you will, where I can solve simultaneous equations or systems of equations by just plugging them into my calculator and away we go. And if that's the case, then great. If you're allowed to do that in the physics course that you're taking, then plug away and come up with the answer. If you're not allowed to do that, or you don't have one of those calculators, then we're going to have to do it the manual way, which we're going to do now. Okay, so at this point what we want to do is we want to solve our equation. So let's just slide the board down a little bit here. And so we have our 3 equations. We have the first equation, I1 plus I2 equals I3. And if we look at the next 2 equations, we have I1 here and we have an I3 here. We have an I3 here and an I2 here. So what I'd like to do is I would like to get rid of, if you will, the I2 term, and I'm sorry, the I1 term, and I would like to replace it in terms of I2 and I3. Okay, so I want to solve for I1 in terms of I2 and I3. Well, I can do that because equation 1 up above has I1 plus I2 equals I3, or we can say that I1 is equal to I3 minus I2. Right? So now what I can do is I can substitute I3 minus I2 in for I1 in equation number 2, which gives me, so I'm going to take this, bring this down here. So I'm going to have 10, and I'm going to remove the units, minus 5 times the replacement for I1, which is I3 minus I2. I3 minus I2. okay, minus 10 I3 is equal to 0. Okay, so I'm getting somewhere. Now let's take and expand all this out, and this gives me 10 minus, well, I've got a minus 5 I3 here and a minus 10 I3 here, so I've got minus 15 I3 minus, the minus is going to turn into a plus 5 I2 is equal to 0. Okay, so I've got an equation here. I'm going to take and write this up on the right-hand side over here, and I'm going to move the 10 to the other side. So I've got minus 15 I3 plus 5 I2 is equal to minus 10. All I did was I subtracted 10 from both sides. So that's one equation. Now I can look at equation 3 up here. All right, it has an I3 in it and an I2 in it. All right, so I'm going to use that equation as well. I'm going to take and I'm going to move that over here. All right, and I'm going to move the 5 volts over to the other side. So this becomes positive 10 I3 plus 4 I2 is equal to 5. Okay? So I've got two equations, I've got two unknowns. It would be nice if the coefficients of one of these were the same, but they're not. So what I can do is I can multiply the second equation here by a factor of 1.5. If I multiply both the left-hand side and the right-hand side by 1.5, what I get is 15 I3 plus 6 I2 is equal to 7.5. Okay, and then I'm going to move this equation here down here. All right, and I've got negative 15 I3 plus 5 I2 equals minus 10. All right, now I can add these equations together, and what I get is I get 0 here plus 11 I2 is equal to minus 2.5. And when I do the math here, I get minus 2.5 divided by 11 gives me a current for I2 of negative 0.227. So I2, let me move this down here just a tad, I2 turns out to be negative 0.227. So guess what? We guessed wrong on the direction of I2. We thought I2 was going to be going up and to the left. Well, in fact, it went in the other direction. All right. The voltage from this power source overwhelmed the voltage from this power source, and the current coming into this junction, actually some went down through the 10 ohm resistor and some went down through the 4 ohm resistor. So we guessed wrong, but it's not a problem because the answer simply turns out to be negative. All right. So we have I2. All right. How do we get I3? Well, it's easy at this point because now we just take and plug I2 back into one of our equations. So I'll use, say, this equation here. So 15 I3 plus 6 I2, well, I2 is negative 0.227, is equal to 7.5. Okay, and then solving for I3, I get a value of 0.591. Oops, 0.5. Let's see if we can draw that in there. 0.591 amps. Sometimes what happens is I hit the button on the pen and it stops writing. All right, so if we know I2 and I3, we can certainly get I1 because I1 is equal to I3 minus I2. All right. And so we have I3, which is 0.591 minus 0.227. Whoops, I hit the button again. And I get a value for I1 of 0.818, I believe, yes, 0.818. And so we have now solved for the currents for our circuit up here. All right, so I hope that helps. Let me move this back down here so you can see these values again. So this is how we solve a Kirchhoff's voltage rules and current rules problem. Again, I hope that helps. If you would like to see this in a PDF format, I've got that out there on the website as well. And we'll see you next time.